Hello everyone, and in today's video tutorial we're going to continue our discussion on motion graphs. Last day's lesson was looking at velocity time graphs, which we were kind of broadly familiar with from National 5. We're going to go on today and look at displacement time graphs. Okay, similar to distance time graphs, just showing you the distance covered over a period of time. The only difference being that displacement being a vector quantity, it means that sometimes the displacement might be positive or negative. Okay, and remember the displacement is always measured from the reference point from the start position. So let's have a look at the first. We're going to just look at the same three motions that we looked at for velocity time graphs, but for displacement time graphs. So starting off with the car moving at a constant velocity, you might want to pause the video here and try and draw in what the graph might look like. So the car is going to start from here and then just going to travel along at a constant velocity. So maybe a bit surprising, not the same as the straight horizontal line that you get for constant velocity, but instead you get what looks like the one for velocity time graphs as a constant acceleration, but it's different on the displacement time graph because what we're seeing here is that the position of the car is changing over time, but it's changing at the same rate. Okay, so as time goes forward, as time passes on, the car covers the same distance, if you like, each second. So if you go in the first second, the car covers 3 meters, and in between 1 and 2 seconds covers another 3 meters, and between 2 and 3 seconds covers another 3 meters. So that's indicative of an object which is moving at a constant speed. Right, the rate at which the displacement is changing is staying the same. Okay, and it's getting further and further from the start position, which is here. Okay, so hopefully that makes sense. Just a wee point, just on the right hand side here, it says that the gradient on this line is actually the velocity. So if you were to work out that gradient, what the gradient would be telling you is the rate at which the displacement is changing, which is the change in displacement per second, or the velocity basically. So if you were to work out this gradient here, it would tell you the velocity, and you can see the gradient is not changing, so that indicates that the velocity is not changing. Okay, it's also a positive gradient that points out as well, and that's telling us that it's a positive velocity because the car is at all times moving to the right, and we're saying that to the right is positive. What I'll do just in a wee second, I'll just add the two graphs for the velocity time graph, the one that we looked at last day for this type of motion, and I'll also add at the bottom the corresponding acceleration time graph, and I'll do that for the other two motions as well, just so we can have a look at comparing the different motion graphs. So first of all, the velocity time graph. So you'll remember that for the velocity time graph for a constant speed just looks like that. So that's the corresponding velocity time graph to match this displacement time graph. Okay, and remember that this value for whatever the velocity might be here, well, it's actually 3 meters per second, isn't it? So that would be a value of 3 on the y-axis there, because it's covering 3 meters every second, and that's not changing. Okay, so it stays at 3 meters per second because we've got a constant gradient. The gradient is equal to 3 on here, and therefore the constant gradient tells us that the velocity is constant. Yeah, you might want to have a go at plotting what you think the acceleration time graph might look like. Okay guys, so what do you think then? Acceleration is, well, it's not accelerating, so the car is not speeding up or slowing down, so the acceleration would in fact be 0. Okay, so you'd have to show that just by a line along the x-axis there. Okay, so there's no acceleration. So that's the three graphs together then for the car moving at a constant velocity. Right, so in this one we're going to see the car accelerating. Okay, so starting from the same position, but this time the speed and velocity is increasing, okay, as the car goes left to right. And remember what we're looking at here is the displacement time graph. So again, you might want to have a wee think about what that might look like, and we'll just run through the the sketch of that graph on the screen here. That's surprising. So we haven't really seen anything like that up to this point, where we have a gradient that's changing. And the reason the gradient is changing is because the car's velocity is changing. So what we're seeing here is that the car starts off at rest, so you'd have pretty much a level zero gradient at that point, and then the gradient starts to increase as the car moves forward. And remember we said in the last slide that the gradient, whatever that might be here, is actually equal to the velocity. So you can see this is indicating that the gradient is positive but increasing. So it's a positive velocity, i.e. moving to the right, but that velocity is increasing, so it's accelerating. Okay, so that's your displacement time graph. A bit different from what we've seen before. And what we'll do as well is we'll just have a wee look at what the other two graphs that match this for velocity time and for acceleration time. I'll just add those just now. Right, did you guess what these two graphs would look like? So the first one, the velocity time graph. So remember we said that the velocity should always be positive, which means it's on this side of the graph here on the above the 0 on the y-axis. But it should be increasing in value. So increasing, but at the same rate. Okay, is what we'd expect to see there. So that's your corresponding. You remember that from the last slide anyway. So that's the graph for a constant acceleration. So like if you had the wee smart car on the trolley and you were just to allow it to roll down the ramp. Okay, just under the force of gravity. Alright, so what does that mean then for the acceleration time graph? Well, this time the car is accelerating, but at a constant rate of acceleration. So the car's speeding up, but the rate at which it's speeding up is constant. That's what you're seeing on your straight line there. So yes, the velocity is increasing, but at a steady rate, a constant rate. So that means that your graph for your acceleration time would be positive acceleration but constant. So if you look at these three graphs then, what we're actually seeing is that the gradient on this one, the gradient on displacement time graph, is equal to the velocity. Okay, so whatever the value is for the gradient here, that would be the corresponding value for the velocity that you're seeing here. So you can see that this gradient is larger than the first one, so we're higher up the graph, and again, higher up the graph. Okay, the gradient on the velocity time graph, so this gradient here, which would basically be v minus u divided by t, that gradient is just the value for the acceleration. So the gradient on that is constant because it's a constant acceleration. Hopefully that makes sense, guys, how the three graphs tie together. We're going to have a look at the last one, and there's a wee bit more detail to this one, and this is where the trolley or the car is decelerating to begin with, but then begins to accelerate back towards the start position. Right, so we're going to start off again with the displacement time graph. So this is for basically if you were to take the car or trolley and roll it up the slope and allow it just to decelerate on the way up under the force of gravity and then accelerate on the way back down. Okay, let's have a look at what the displacement time graph would look like. See how many of you are able to get this one. So that's quite difficult to understand what's going on there. So yeah, again, what you need to do is look at the gradient on the displacement time graph. So you're seeing that the gradient starts off with a positive value. That's when it was given a push up the ramp, but then that gradient begins to decrease, and it actually tends towards 0 at the top here. So where the gradient is 0, remember gradient on a displacement time graph is velocity. So we've got positive velocity, large value, smaller value, 0 velocity. So that's the point at which the velocity of the car is 0. So it's up here. Okay. To try and make sense of the second half of the graph, what we've got is we've got the velocity now becoming negative. So, well, the gradient's negative, remember. So if the gradient is negative, it means the velocity is negative. So we're starting off top of the ramp here at 0, and then it begins to become more and more negative. So the gradient is becoming a larger negative value, larger negative gradient on the graph there, and that's telling us that the speed is increasing, but it's moving this way now, so it's moving down the slope. So hopefully that makes some sense. We're going to try and just tie in with that what the corresponding velocity time graph and acceleration time graph would look like. So here's the velocity time graph. So hopefully you remember this from last day's slide, where it's showing you that if the car starts off with a given velocity and whatever this gradient is at the start here, so that's this gradient on the displacement time graph, that's telling you the velocity. So say that was, let's just say that was 20 meters per second. So at the start here, car's going at 20 meters per second. It means that it then slows down, so decelerates until it reaches a velocity of 0. That's at the top of the slope here. And then it begins to move in the opposite direction, and eventually it should reach, provided that friction is small enough that it doesn't affect the motion, then it should end up travelling at minus 20 meters per second by the time it gets back down to here. So that's it when it's come back down again. So hopefully you can see there that as well as, remember we said last day, you can work out the displacement from the velocity time graph. So if you wanted to work out the displacement from this graph, then you're working out the displacement from when it started to this end point here, which would be 3 seconds in. Now, like I said last day, you would do that by working out the area underneath the graph here, and you would add those two areas together, and that would give you a displacement of 0. And that's consistent with what we see on the graph, because 3 seconds in, we're saying that your total displacement is 0, because that positive area plus the negative area that you would get from here would cancel each other out, and you would have a displacement of 0. Now if I follow across to 3 seconds on the displacement time graph, that's consistent, because you can see here that displacement has gone back to 0. Okay, the displacement wasn't always 0. At different times in the graph, the displacement can be given by these points here, but after the 3 seconds are up, the displacement of the car is back on 0. Okay, which is consistent with what you would get if you were to find the area underneath the velocity time graph. So kind of lots going on there, but we can see things that match up between the two graphs. So like there, for example, is the highest point on the slope where the velocity is 0. That corresponds to here where the gradient on the displacement time graph is 0. Okay guys, hopefully that makes sense. We're just going to add the last graph, which is the acceleration time graph, to go with this, these two velocity and displacement time graphs. Right, acceleration time graph. Maybe you've been able to figure out what this last graph would look like. And remember that the gradient on here, on the velocity time graph, just gives you the acceleration, or in this case it would be a deceleration. So that's a negative gradient there, which means that the acceleration is negative and constant. But you do notice that when it crosses over to the negative part of the graph, it doesn't change. So you still have the same slope, the same gradient, and it's still a negative gradient. So that means that the corresponding acceleration time graph is just going to be a constant negative acceleration. And that's probably the one that folk find a wee bit tricky to understand, because at National 5 we would quite often think about if an object is decelerating, like the car is on the way up, then we would say that it has a negative acceleration, which it does here. But then when the car starts to roll back down the ramp, it's actually accelerating. So you might have thought then it should switch to a positive acceleration. But what we're going to find as we kind of explore equations of motion and motion graphs at higher physics is that it's no longer it's not the case, it wasn't the case, that a negative acceleration always meant slowing down. A negative acceleration only means it's going to slow down if the car is moving in a positive direction. So you've got a negative acceleration acting on the car. The reason for that is because of the force of gravity. The acceleration acts in the same direction as the force of gravity acting on the car. So because the force of gravity acting on the car acts down the slope, so that means you've got a force acting down the slope, and that means that that's the direction of your acceleration, because remember, acceleration is a vector quantity, so you've got an acceleration which acts down the slope. In other words, it's negative, and it always acts down the slope because the force always acts down the slope. So what this means is that you have a negative acceleration as the car makes its way up. The effect on that is to slow it down, and that's because the car is moving in a positive direction. So if the velocity is positive and the acceleration is negative, then it causes a deceleration. It causes the car to slow down. However, once the car reaches the top of the slope and it then begins to move in this direction, that means that the velocity is negative and the acceleration is also negative. And when you have a negative acceleration acting on a negative velocity, it makes it become more negative, so it makes it speed up or makes it accelerate. So you should no longer be thinking of a negative acceleration as always meaning slowing down. It will mean slowing down for the first part of the graph because the car has a positive velocity in the first part of the motion, but it will mean accelerating or speeding up when the car is moving down the slope in a negative direction. I hope that makes sense, but you can see from the graph that the gradient's not changing. So that means that your gradient is always negative. On the velocity time graph, the gradient is always negative, and that means your acceleration is always negative throughout. It doesn't change. Okay, so hopefully that's covered everything that we need to cover on the different motion graphs. There probably will be some questions on this. Let me know, send me a message on Schoology, and I can go over any of the stuff if you need me to. But I think we probably need to spend a wee bit more time just practicing some tutorial type questions on these different motion graphs, especially the displacement time graphs, because that's quite new. And the velocity time graphs are a bit more complicated than what we looked at in National 5 because they consist of positive velocities and negative velocities. Also, guys, there are notes in your booklet 1A just on the different motion graphs, and it shows all of these motion graphs for the different scenarios for constant velocity, for constant acceleration, and then for a constant negative acceleration, which is the one that we've looked at in this last slide here. So have a read through those notes. I think there's a couple of worked examples there as well, and then we'll spend a bit more time on tutorial questions on motion graphs.